So the title's a mouthful, but essentially what we wanted to do was share our lessons learned when we migrated our monitoring system from a classical architecture to a new architecture, which was largely based on standard big data technology stack. Okay, so it's really just about our experiences, what we saw, and we thought that would be of very high value to this audience. Before we begin, let me introduce ourselves. So Mridul Jain, my co-speaker, he's a senior principal architect in the machine learning team, the big ML team, and he was one of the architects on the monitoring system when we were revamping that. He's also the co-author of recently released Caffe on Spark library from Yahoo for deep learning, as well as Pig on Storm. My name is Sumeet Singh, and I lead products for Yahoo's big data platforms. And of course, we're here on the stage talking to you about revamping the monitoring system, but this would not have been possible without the work of two Guptas, actually, ironically. One is Arun, and the other one is Kapil, and they are architects currently on the monitoring system, and they do a lot of work in this area. And then, of course, the entire monitoring team, as well as the big data platform team at Yahoo. Okay, so definitely want to acknowledge their contributions. And let me outline an agenda of what we plan to cover. So I will give you a very sort of high-level overview of the monitoring system then, the monitoring system now, and how we sort of transition that old stack to the new stack. And then for the bulk of the talk, we'll get into the specifics of lessons learned as we worked with Storm, Kafka, and other things, right? What are the types of things we observed, particularly at scale? What were the challenges and how we dealt with them? And then if you have time left, we'll open it up for Q&A. So this is a very high-level overview of what monitoring means for a web-scale cloud. So we have hundreds of thousands of hosts literally spread across multiple data centers all around the globe. And then the monitoring system actually is meant to monitor both that infrastructure that I just described to you, as well as the applications that run on that infrastructure, right? So we're interested in both infrastructure performance as well as application performance. And those are the types of things you would monitor, essentially. And this is all online. But the beauty of the solution is that it's offered as a hosted cloud service to the rest of the company so that they don't have to go and reinvent and redig and sort of resolve the problems that we have solved at scale. So people just sort of use it as a self-serve platform for monitoring their infrastructure, their applications. Right, so it has lots of components. There are collectors, aggregators, dashboards, things that you would normally need out of a monitoring system. And that's all built in as a cloud service, okay? So this is what the classical architecture looked like. As I mentioned, roughly 200,000 hosts sending billions of metrics every day that needed to be tracked. And so this was the monitoring solution before. Through a distributed load balancer, the various collectors, which are essentially HTTP servers, would collect those metrics and pass it on to aggregators, who would then sum up those raw metrics into something a little more sizable, and then pass it on to DB shards, where those metrics will be stored for further analysis, slicing and dicing of data, or dashboarding, drawing charts and stuff, right? So what you would observe here is that in this architecture, we had an issue of a massive fan out. So from the collectors to aggregators down to the DB shards, there was a massive fan out. The other issue was that just the way it was architected, the shards had to be constantly manually adjusted. And that was a problem. And then finally, if you look at the query layer, it generally would hit multiple shards, many shards, sometimes sequentially, which was also an issue for query federation and response times of those queries, right? So clearly, this architecture had manageability challenges for us. We were dealing with it, but it had challenges. The other issue was that the hosts were manually partitioned into the notion of what we call clusters, which was essentially think of it in database terms or in relational database terms as the database itself, the namespace. So we call that clusters. And that concept was important to plan capacity, plan resources for a particular tenant. But the issue was that the hosts had to be manually partitioned into those clusters. The other issue was that the aggregator process for cluster was a single-threaded process. And it actually, what that meant was that if you have specified rules of how you monitor the metrics, then those rules were processed sequentially. And that introduced a scale limit, so we were only able to aggregate 4 million data points a minute, right? And then the third issue was that there was at least a shard per cluster. And then that introduced yet another scale limit of, let's say, 1.5 million data points for reads and writes off of that shard. And then finally, I described to you the way the dashboards were written that would incur a sequential fetch for queries when you're drawing dashboards and charts for the data you're monitoring, right? So what you would see here is that there were very clear scale challenges. As more tenants onboarded to this system, this hosted system, it started to hit scalability bottlenecks. And then we had a hot BCP across multiple data centers for this system, but the components of the system within the data center were not highly available. So there were availability challenges as well, right? So you had to manually switch over or fail over to a BCP instance should something go wrong. So 3 issues, very simple issues of manageability, scalability, and then availability had to be addressed. And one simple way we dealt with it was that we replaced the problem items with standard big data tech stack. So for aggregation, we started to use Storm and Kafka, and then for storage, we used OpenTSDB backed by HBase for storage, right? So that's essentially what we did. And the components that were not in problem, like the collectors and stuff, stayed the way they were. So what you would see is that the manageability was taken care of because most of these frameworks are horizontally scalable. The scalability itself was taken care of as well. No more manual partitioning or management of tenants in sort of a crude way was required, as well as these components had built-in HA, so it took care of the availability within the data center. So the idea, again, was very simple. What the collectors would collect data for multiple tenants, but we would aggregate that in a Storm topology, all that data, and then start to separate it into individual Kafka topics per tenant, right? So that's where the first Kafka stack came in, where you're now separating per tenant topics or data, and then individual tenants ran topologies in an aggregation cluster, a separate Storm cluster. So each tenant would run its own topology that would take data from the tenant's topic in the Kafka cluster. It would further send that data down to another Kafka cluster, and Mridul will get into the reasons for why that is needed. And eventually, all that will flow into TSDB, which is backed by HBase for storage. And then the dashboards and other things were revamped as well to sort of mimic this paradigm. So as you can see, this whole stack now is literally a low latency real-time system now, which it was before as well, but with those challenges that I described to you. We were able to scale up the system from 3.5 million data points a second to 20 million data points a second, so a 5x scale up just by revamping some of the components in our architecture. And then this gives you massive parallelism as well as pipelining. As you see, everything sort of streamlined. And then the alerts and thresholds before had issues as well. Sometimes it would cause delays or drop notifications before because there was a poll-based system before, and now that all became real time, triggered directly from the Storm clusters. And then the HBase, we were only able to go 2 weeks back in the previous system when we're doing historical charting, and now you're able to go back almost a year in terms of the metrics you want to look at. It also started to support this complete idea of a self-serve system where most of it is programmed by the tenant, so we're not involved in the way. We'll just show you how. The topology, tenant-specific topology that ran for aggregation, for rollups, processing their rules, and other things, also did an interesting thing where actually the whole sort of stuff became pluggable. So you could have your own anomaly detection algorithms pushed in as Storm bolts EGATS is a good example for anomaly detection, which is also something we've open sourced. So all that pluggability became really interesting for tenants that had specific needs. And then I mentioned self-serves a couple of times, so this is how we accomplished it. We built a higher level language on top of Storm that would specify the operators and other things that people were interested in looking at. So they would specify their rules, and we would automatically push all that into Storm and deploy that as a topology in a very hot fashion. And the alerts and other things would be triggered right out of Storm. So that also became quite real time. As the aggregation's happening, you were hitting certain thresholds, you would get alerted to specific emails or whichever mechanism you have specified in this self-serve path. Okay. If just in case you're curious of what that language looks like, it's just a high-level specification, but it's rich. It has most of the operators or standard operators that you would need in a monitoring system like group by, join, and other things. You could also join multiple namespaces. So a lot of simplicity here in terms of how you want to define your aggregation rules, but yet at the same time, it sort of leverages the power of the big data stack in a very simple way. With that, let's get into the specifics of the lessons learned as we did this. And I'll hand it over to Mridul.
Thanks, Sumeet. Can you hear me? Okay. Can you hear me okay? Okay. Okay. Okay, cool. So let's get into the lessons directly because we're at the time. So first one is producer-consumer problem at scale requires the right balance in architecture. So before we go in there, just a quick overview of the Storm. Storm, as you know, is a real-time processing framework where the data is acquired from external data sources by spouts, which push it to the bolts. And they process the data and then push it downward to a DB or storage, or in our case, Kafka. And Kafka is a real-time stream processing system. Kafka is a real-time queuing system which has brokers, and each of the brokers have topics. So producers write data to the topics, and consumer consume data from the topics. Now, just to give a sense of the scale at which we operate, we have around 450 Storm topologies with 15 topics per topology and 3 partitions per topic. And the partitions ensure the read-write parallelism. We have around 400 bold tasks in the ingestion topology alone, not the user topologies. And we are processing around 20 million metrics per second in this particular system. So coming to the exact producer-consumer problem, so Kafka has this particular notion, Storm has this particular notion that you should not have any kind of intermediate brokers in your processing pipeline because it slows it down and it is difficult to maintain. So Storm works as an excellent system, processing system for us, which consumes the data from external data sources, processes it, and pushes it to downstream. But this problem becomes extremely complicated at high scale. And in an end-to-end system where other components are most of the time trying to just match up to Storm's scale. So here we have a multi-tenant hosted HBase, and our HBase always has issues trying to match up to the writes from Storm. And that is the reason we use Kafka in many places, including this one where we use it as a queuing system just to synchronize the two. Now, so Kafka actually provides a good end-to-end synchronization mechanism for us in our whole pipeline without loss of performance, and it also gives us a breather against individual component failures. Now, apart from that, a good queuing system, or Kafka for that matter, can help scale individual components in your tech stack. So for example, we have this topology called time rollups topology. So topology, by the way, is just a DAG in a workflow, right? So we have this time rollups topology in Storm where we have all the data coming into our system, and that data gets aggregated on a specific time series, which is a unique combination of metrics and dimensions. And we provide 4 kind of aggregates out of the box because these are most commonly used. One is sum, min, max, and count, right? So in this particular topology is written in Trident, and Trident is a high-level abstraction on top of Storm. And it optimizes Storm to a large extent and provides easy onboarding. Now in Trident, this particular, in this particular topology, you have the spout, which is consuming data from the topics, Kafka topics. So you're consuming around 220 million metrics per minute, right? And then the spout tries to push it to the Storm bolts. But in Trident, this completely fails, just because it cannot push so much data from the spouts to the bolts. It works in normal event processing systems in Storm, but not on Trident. And so we have to do most of this kind of aggregation in the spout itself. But if we do that, then who's going to do the group by or partition or fields grouping on the time series, right? Because the way it works is the bolt is supposed to do a group by or fields grouping on time series, and it is supposed to aggregate the data. But since we have the whole logic in the spout, who's going to do this particular thing? So this is where the Kafka producers come in handy. So the Kafka producers basically take each of the time series and then do a fields grouping on that particular time series and push it to the topics. And these topics, from these topics, the spouts consume the data and aggregate that particular data. So this is one of the examples where a queuing system can help scale a topology or any other big data stack. But what if the queuing system itself has issues? So I would like to point out one of the issues here called Kafka refresh. So Kafka has brokers or servers which host topics, and every broker has information about all the topics in the Kafka cluster, right? So a producer basically can, which is writing data to a broker, while it's writing the data to the broker, once in a while, that is every 10 minutes, I think, it goes and refreshes the topic list. And it can ask for any number of topics, topic list from the broker. So every topic fetch has a timeout of around 10 seconds. And this is a blocking call for the producer, which means there's no data written while this particular call is going on. So suppose a producer is trying to fetch around 100 topics from a broker, and the broker has gone for a toss, or it has a socket timeout. You have an overall aggregated, timeout of around 1,000 seconds, and by which time the next 10-minute cycle, a refresh cycle kicks in. So effectively, the broker would hang, the producer would hang, and the whole system hangs, because at this RPS, most of the producers are writing data to most of the brokers, and which means all the producers at some point in time or the other would write the data to a specific broker, right? Which is timed out already. So Kafka overall has served as an excellent queuing system for us, and there is great community support from Kafka. But the point to drive home here is that, by the way, one of the things which you can do is you can try to do a disable of refresh on Kafka, but you would get into issues because it becomes much more complicated. The way we try to solve this particular issue is using a load balancer or WIP. So anyway, the point to drive home here is that a good queuing system is your last line of defense in a real-time processing pipeline. So you need to choose it wisely. If you choose anything other than Kafka, you are pretty much on your own, because at this rate and this kind of data, most of the systems I have worked with don't scale. The second one is skewness in data is hard to debug. So most of you know that scale is directly proportional to RPS in a particular system and the cardinality. And we all know the curse of cardinality, right? So, but I'm going to argue that low cardinality data at high RPS can create havoc in the system. So we have a specific Storm topology here, which is ingesting around 22 million metrics per minute here. And every event here has one specific dimension which is common, which is data center. And the data center has two values exactly, east and west. So what we are trying to do in this particular topology is trying to aggregate the data by a particular data center. Now, the bolts in layer A do a fields grouping on this particular dimension, and then push all the data for a particular data center into either bolt B1 or B2. And bolt B1 and B2 being single tasks, they have to maintain so much state for this kind of RPS, and they of course blow up in terms of memory. So the simple solution to this particular problem is that you can have combiners. The combiners, the way you use it in MapReduce. And combiners will do partial aggregates on each of on the data centers, and then push the aggregated data only to bolt B1 or B2. In this particular way, you solve this particular problem because the aggregates are very small in terms of the footprint. and the problem is solved. But the interesting question here is, when you deploy a topology in production, should you deploy with combiners or not? Now, if you deploy it with combiners and your cardinality is very high, you are pretty much going to require 10x the size, 10x the memory footprint, just because you're going to aggregate the data for each of those dimensions, right? And if you do not deploy by default the combiners, you will get into the kind of issue which I was talking about. So the way we figure this out right now is, it's a tricky situation. So the way we figure this out is, whenever we find a problem in any of the topologies, we look at the data skewness and pretty much push in a combiner on the fly. Of course, there is a restart of the topology, and we do not lose data just because of the fact that the data is still maintained in Kafka. Of course, everybody knows the curse of cardinality, so I'm not going to get into details of this, but it hits us in two places specifically. One is Storm. So in Storm, it is very difficult to manage most of high cardinality data and state around it. And the second one is the UID table, which is required by OpenTSDB and is maintained in HBase, right? So this is a table which converts all the keys in our data, which are in strings, to numbers for efficient storage in HBase. And this, the higher the cardinality, the more unique number of strings, and more frequently you're going to hit the UID table. The third one is multi-tenancy and resourcing. So resourcing is one of the most difficult things to get right in Storm and any real-time system, because you do not have any rules. All you have is a bunch of heuristics or your experience, right? And as far as multi-tenancy goes, each of the big data components are supposed to be horizontally scalable, but when you combine everything end to end, it just doesn't scale. You need to apply your own, rework your own architecture. You need to apply your own heuristics and strategy to just make the whole thing work. So one of the examples here is Zookeeper. Now, everybody knows that Zookeeper is a bottleneck. Although it is central and core to most of the big data system, it is still a bottleneck, because every write gets replicated in the Zookeeper quorum. So earlier we used to have a single cluster of Zookeeper, single quorum of Zookeeper for Storm and Kafka, but it just didn't scale for our topologies and Kafka, because specifically Kafka can create havoc in Zookeeper because there is a lot of state churn which happens. So most of the state for the consumers in a consumer group in Kafka is stored in Zookeeper. And whenever a consumer enters or leaves a group, it creates a churn in Zookeeper state. So to just give an example, we have around 250 TSDB instances, part of a single consumer group consuming from the Kafka, right? And that's the way you would actually consume from any Kafka cluster. And of course, even in steady state, each of these consumers will enter and leave the consumer group, which creates a heavy churn. So the simple solution to this particular problem is to, of course, have separate Zookeeper quorums for Storm or Kafka, or look for other alternatives. In fact, I think in the latest versions of Kafka, Kafka is trying to move away from storing the state in Zookeeper and then putting it in maybe a broker itself, right? Now, this is just illustrative. You can have any number of Zookeeper quorums that you want, depending on how you shard your clusters. But it is difficult to manage. So this is one of the challenges, right? Zookeeper is supposed to scale, everything is supposed to scale, but it just doesn't. And you need to apply your own heuristics here as to how, depending on how your business needs are. Another problem is topology scaling. So most of the users deploy topologies in our system in a self-serve fashion through our language. They just deploy the topology. And we have around 450 topologies. So earlier we were running a single Storm cluster, which just didn't scale to 450 topologies. And on top of that, Trident has this particular issue where it cannot run more than 400 logical bolts in a topology. And we have people and workflows which have around 1,200 bolts too, right? So these two are big challenges, and it leads to all kinds of problems. A rule is equivalent to a bolt. So a rule in our language is equivalent to a bolt. So we had to actually have separate clusters, one cluster, different clusters on namespaces, a separate cluster for roll-up topologies, a separate one for system abuse topologies, which actually monitors this whole monitoring system itself. The third example which I wanted to give here was about HBase. So I said in the beginning of the talk that HBase has very hard time always trying to match up to Storm's producers and Storm's write scale, right? So we used Kafka here and everything worked pretty well in the beginning. We had, but as our RPS increased and the region sizes for HBase increased, HBase started getting into a lot of issues. So you started seeing these things like region splits and hotspots, NSREs, GCs, unresponsive regions, unavailable regions, etc. And we worked pretty hard actually to fix most of these issues in HBase. And after some time, we realized that this is going to be the steady state of HBase at this type of RPS. And we had to make that assumption and work around it, work our architecture around this, right? Earlier, we used to have a system where Kafka consumer will consume the data from the Kafka topics and push it to HBase via TSDB. And you'd basically get into these issues. The UID table, which I just talked about, no responses from HBase, non-serving regions. This is such a pain just because of the fact that your workflow works pretty well, but your storage system just doesn't scale, right? So what we had to do is actually requeue most of this topic in Kafka, these messages in Kafka. And then both of these messages, the topics, the messages in Kafka, as well as whatever we had in the real-time pipeline were consumed parallelly. This has helped us reduce the data loss from around 20% to 0.5% in our pipeline. And this is something, again, just architecture rework, right? It has nothing to do with automatic scaling of systems as we put together all the big data systems together in an end-to-end system. The fourth one is optimizations made in asynchronous systems are hard to debug. So this is about retries and auto fixes and the smartness that we try to have in our systems to auto recover. So this could be self-created, but it is worth discussing still. So we write data from TSDB to HBase in a synchronous fashion. So these data points that we write are called RPCs. And you have a TSDB writer thread pool which writes data to HBase asynchronously. And because it is asynchronous, we need to store that particular RPC in our Guava cache, just because we do not know whether the call has succeeded or failed till the time we get a response. So if we get success, we just evict that particular RPC from the cache. So everything is fine. If we get a failure, we basically do a retry of the RPC by looking up that particular RPC ID in the Guava cache. So this is also fine. The problem happens when you get timed out RPC. So the Guava cache also maintains timeouts on RPCs. So if a RPC has timed out, it is going to call your handler, a custom handler, where you can do whatever you want. And the Guava cache does not have a thread of its own, so it runs in the context of the writer thread pool or the native thread pool. So whenever you get a success or failure, and whenever you do whatever in success or failure, as I spoke earlier, the Guava cache, if it has any timed out RPC, it is going to use the same thread, latch onto the same thread, and call the user handler to say, can you handle this particular RPC for me? And what we typically try to do in this particular case is we take this particular RPC and push it back to HBase and retry it again, right? And this doesn't happen all the time in the sense you retry it like twice or thrice or whatever, either in phased cases or in case where we have RPCs timed out. So this is supposed to work pretty well, except that when the number of timed out RPCs are pretty high, that thread never gets actually freed. The moment you get a response for success or failure, you get these callbacks to handle the timed out RPCs, and this whole thread goes into a recursion, and you get stack overflow error, right? So the problem is, this doesn't happen all the time, but it happens once in a while. And apart from what you have done here, the bigger problem is how do you debug such a problem, right? Because all we are seeing as manifestations of this particular problem is that, we have stack overflow error, and that's it. And TSDB hangs up, which means how do we put the two things together? So what we did basically is we knew that when something hangs, it could be a locking issue, and we already see a stack overflow error. So we simulated this by making sure that every time we have a recursive call, we do an unlock and lock on the Guava cache. And so every time you have a recursion, you will do a lock and unlock. And at some point in the recursion, it so happened that the lock got hit, and when we tried to unlock it, there was no space left in the stack. And when that happens, the lock does not get freed. Similarly, for the next lock, it will not get freed next stack because there's no space on the stack. And then we start getting more space on the stack just because we have unbounded. So, but basically the owner thread would die because this is a Stack Overflow error, not just an exception, right? So this is the end state. You have the thread dead, 3 locks remaining, and the cache is logged, and the writer thread pool cannot write anything to HBase because the Go cache is logged, and TSDB is hung. So debugging these problems in asynchronous systems is very hard, specifically if you try to do too many auto retries and auto fixes. The last one which I wanted to call out was about your application optimization. So basically, you try to have your applications written in the most optimized fashion. You try to make sure that there are no bugs, etc. But you need to be also aware where you are running this particular application, how it interacts with the OS, and how it actually interacts with other components in your tech stack. So this is one of the examples where we can consider this Bolt as our application, which is writing data to Kafka producers. Now, if the Kafka producer is dead, you are going to be smart enough in the Bolt to just take that particular write and write it to another broker in the system. But if the Kafka producer has accepted your connection and it is slow and it has gone down because the disk has gone down, or it is extremely slow, it is not responding, you are pretty much, your thread will primarily hang because you are doing a write on the socket, right? And nothing can be done here unless you have watchdogs which can kill the thread, and the whole solution becomes extremely complex. Now, here most of the writes will stop, and as I said, most of the producers are writing to most of the brokers. So essentially, the whole topology at one point in the time or the other will go down, just because the upstream cannot match up with the back pressure. Now, this is a simple problem, but neither a problem of Kafka nor the problem of your own application, but nevertheless, it exists. And it is very difficult to debug. At the same time, it is very difficult to fix also, because you can write very complicated solutions around this to do similar kind of auto retries and fixes, even in a synchronous system, but you would get into a lot of issues. Right now, what we do is just monitor this well, and if there are problems, then we have to restart the topology. But of course, you can invest a lot of time and effort in this just to have watchdogs to kill your threads and do all kinds of hacky stuff. Just don't know what's the right balance here. The last one which I wanted to point out was about Kafka Broker itself. So Kafka Broker has the JVMs which store information, or it has the memory about the broker code, read variables, file handles. Writers, the producers are writing the data to the Kafka broker itself. And this particular data is going to be written to the disk. And because this is written to the disk, the OS caches the pages automatically. So Kafka has this brilliant design where the readers or the consumers are going to consume the data from the OS page cache itself. Because you are anyway going to have this cache, irrespective whether you want or not, because you're writing the data to the disk. So OS is going to cache it. So if you're doing this cache, then why should you maintain this data or another cache in the JVM for the readers, right? There's no point, because JVM and caching doesn't go hand in hand. Secondly, it will blow up it will require double the size of memory in JVM because the Java objects, right? And the third piece is if the JVM goes down and comes back up, you don't have the cold start problem because the OS page cache is always hot. So this is a brilliant design of Kafka, and it really scales pretty well. Except that when the OS figures out that there are certain parts of the memory in the JVM or the pages in the JVM which is not being used, it swaps those parts to the disk just to maximize the OS page cache. And this is also great, but till the time the GC kicks in and says, I want my pages back for garbage collection, just garbage collection, not even usage. And you need to swap all that data back into the disk just to do GC. And when that happens, you have, that is of course a very costly operation. When that happens, the JVM hangs, producers hang, and that creates a heavy back pressure upstream. Specifically, you won't see these kind of problems in simple systems where the RPS is low. But when you're dealing with something like 20 million events per second, every such problem is going to blow up 10x, right? And you would pretty much have a disaster effect in your whole system. So there is a setting called VM swappiness in Linux, which is set to greedy by default. And you need to be aware of this. If you're not aware, you will just go in some kind of a black hole. You need to be aware that you need to set it low in this kind of a cases where you are just saying, I know what I'm doing, don't touch my JVM memory at all, right? And this is how we solve this particular problem. But mostly, these are the different lessons that we have learned over time. And there are a lot more which I could not cover here. But if you're interested, I can share it offline. Thank you. So questions? Yeah, Q&A, please. Okay, yeah, sure.
You said that you have multi-tenancy on the OpenTSDB layer, on the HBase. Is that scalability with HBase in OpenTSDB or to your internal environment?
Sorry, I could get only part of the question, actually.
Is the question about HBase being multi-tenant?
Yeah, correct.
Yeah, so Yahoo operates HBase clusters in a very different fashion that you might see otherwise. Some of those multi-tenancy changes have actually gone in. So in the later versions of HBase, as they get released, you will see that. We operate a concept called region groups, where these region groups are assigned to tenants. So it's the same HBase cluster, but that holds, let's say, 50 tenants. One of that tenant could be the monitoring system that's actually writing metrics in TSDB, but the storage of TSDB is backed by HBase. So yeah, there are other tenants in it, but there is an isolation.
And is your TSDB, do you have a single TSDB with an HBase that holds all your monitoring data, or there are multiple OpenTSDB layers?
Oh, so there are around, in terms of instances, there are 250 instances of TSDBs actually writing data to HBase. Because you have around 50 TSDB servers with 4 TSDB instances each, basically.
And this goes in a single HBase tenant?
Yes, hosted HBase, yeah. Yes.
The-
We have around, sorry.
I was just trying to point out that HBase itself doesn't provide TSDB as a service, so it's specific to monitoring. So monitoring actually
Because it's
manages them.
time series data, so we have around 80 HBase servers actually, and 30 for time rollups.
Really large HBase installs, but it's for a lot of different things through the company, monitoring being one user, one tenant of it, the platform.
Yeah.
How do you protect yourself against high cardinality and UUID limit?
Yeah, so this is an excellent question. See, the point here is pretty much every system would try to have some kind of a cap on the cardinality. So earlier in YAML one, we used, our earlier monitoring system, we used to have around 8 dimensions supported with whatever kind of values. Here we say around 20 to 30. Although in reality, when we architect such a system, we do not want to limit people. So of course, you will have to have some kind of quota, but right now the way we do this particular thing is detect during collection what kind of data is coming in. If the cardinality from a particular namespace is pretty high, you pretty much tell them, or you go on till the time you can handle the pressure. There is no simple technical solution to the cardinality problem, actually. Yeah.
We heard a lot of bad things about Storm this week.
Okay.
I was wondering what are your thoughts on Storm? We're using Storm as well and pretty
Okay. So, yes, so this is actually an excellent thing. I've been using Storm for like past 4 years. I have a pretty balanced view about Storm because you have these Samza and all these new things coming up. So Storm, to me, specifically the event by event topology in Storm, there are 2 kinds of topologies: batch processing and event processing. And then now you have Trident, which subsumes the batch processing part, right? So the event by event processing topologies work extremely well in Storm. Storm as a mechanism has been written extremely well. Whatever it is supposed to do initially when Nathan wrote it, it does things very well for whatever it is. Now, of course, the Trident does not do that great a job because I think it was written later as a way to subsume transaction topologies or batch topologies in Storm. But still, it actually scales pretty well. So if you're talking about this kind of scale, yes, you would get into some issues or the other, but I'm sure not everybody is operating that at like 20 million events, 20 million metrics per second. So Storm as a processing workflow works extremely well. But the problems are always about, Storm can do things, but then what do you do for other components like TSDB? Our major pain point here is HBase and TSDB right now. And that becomes more of a concern than Storm itself. So should you have like intermediate brokers in between, like the way Samza says? Yeah, that can help. Of course, you don't have to reprocess everything because here we do guaranteed processing, at least once guarantee, right? For all 20 million events per second or metrics per second. So I think Storm works extremely well for whatever it is supposed to. But I don't know.
I would drop in a couple of thoughts there as well. So we've been working with Storm for nearly 4 years. Probably have the largest Storm deploys anywhere in the world, between 2,000 to 3,000 servers running Storm. All our advertising pipelines, revenue pipelines, almost everything, personalization pipelines for content, all runs through Storm. We have had a lot of success. And we have also kept a tab on how sort of other systems that are coming up, let's say Spark Streaming or Flink, are performing against Storm. So there was no real world benchmark for streaming systems. We actually built one and open sourced it. So if you go to yahoo.hadoop.tumblr.com, it will take you to the Git location. So it's basically will be github.com Yahoo streaming benchmark or something like that. I encourage you to play with it and benchmark it yourself if you don't trust me. But we have had a lot of success with it. And I'm not saying everything's perfect, but we're investing a ton of work in Storm. Largely in the area of multi-tenancy, we're also releasing something called as resource-aware scheduler very soon. The Zookeeper issue Mridul was describing is more or less taken care of. We've taken that out. We've introduced another component called Pacemaker, which is a literal key value pair, and that does the job for heart beating into Nimbus. So there are lots of issues that had existed. But again, I think you will see those issues only at scale. You're not going to see most of it for simple systems, as he kept harping on. So I don't know what the bad things you heard were, but I can assure you that we're pretty happy with it.
Let's give him another round of applause.
Thank you.